Hey, Physics 30s, how's it going? So we're going to talk more about diffraction, and interference of waves as light waves, EMR waves, after they pass through a dual slit, after they pass through two slits. So the Thomas Young's experiment here. So if you watch those videos from Veritasium, help us figure this out. So Thomas Young's experiment, light passes through two waves or two slits, and it creates a nice little interference pattern for us. Okay. So what I'm going to do is I'm going to use this picture. In the next slide here, you can see in the next picture, I've tilted it sideways and kind of shrunk it down a little bit. And we're going to talk about this, and we're going to talk about the next one down here as well. And how do we develop a formula to help us solve certain questions? And the formula only really works because we make a pretty big assumption here. Now, the pretty big assumption is that in comparison to the distance between the two slits, and so this down here is D. We already talked about some of the labeling of these diagrams in this picture here when it pops back up. So D is the distance between the slits, L being the distance from the slits to the screen or the measuring device or whatever it happens to be there that's measuring this wave interference pattern. That's L, and then X being the distance from the center maximum point or antinode to whatever node you happen to be looking at or antinode you're looking at. Okay, so this picture is kind of more or less drawn for you if it shows up or not. Taking its time. This picture is more or less drawn so that you could see more of a scale, even though this is not even close to what it probably would represent, because again, this D is supposed to be really small, millimeters to micrometers, even to nanometers in length. And L, this distance all the way across, this L is huge. So this L is much, much, much bigger than D, right? Maybe a little exaggerated how many much biggers there are there, but it's a huge number in comparison. Now, that's the assumption that we have to make, is that this L is gigantic compared to D. It's much larger. And the reason behind that is that this blue dotted line that you can see that's going over to n is equal to 4, this blue dotted line is from the center between these two dots, and that's measuring this angle here. But that's not really true, because you have to think about these two lines here. They're going off this direction, and they're meeting at this point. So these two lines are technically not parallel to each other, because they will eventually converge to this point over here. And if it's converging at 0.4, this top line is 4 wavelengths longer than the bottom line, because it's at the fourth one, right? So you can think of it the lengthwise between these two. At the very end over here, if I were to line these two up together, this would be 4 wavelengths longer. It's hard to see that, but that's 4 wavelengths longer than the bottom line. So I could put two distance here, like top one's 1, so we can call this, I don't want to use D, I don't know what letter we can use here. Let's just say wavelength, or length 1, sorry. Let's just call this, let's call this LS1, and let's call this LS2. Now, if I go LS1 minus LS2, I should get 4 wavelengths in length, because that is the bright spot. That's the fourth number in the bright spot. Now, if I go down to 1, that would be 1 wavelength, 2 would be 2 wavelengths, 3 would be 3 wavelengths longer. So this would cause constructive interference. That's going to be important for later on too. Now, if I make this assumption up here that L is much larger than D, these two lines beginning over at this end over here, they get closer and closer and closer to each other, and they get closer and closer and closer to each other. LS1 and LS2 become really close to being the same length, because also the wavelengths are really, really small as well in this situation. They could get really, really close to being the same length that you can almost consider them to be parallel to each other. And that's pretty important for creating the formula, is that L1 and L if this is the case, if L, this distance going across is much bigger than D1, we can almost assume that L1, LS1 is parallel to LS2. So they're parallel to each other. Okay, now why is that important? Well, it's important for the formula. So this angle that we have here, if I zoom into this little area down in this little piece here, I'm going to get this picture. So I'm zooming in here. So this is now down here. I'm not too concerned about what's up here. I just know that's a really far distance away. So this is the L distance here. So kind of zoomed in. This central line here goes up to that first anti-bright spot. So this is going to be that L that goes up there. You can see that this angle here, that's from the center over to this node that we're looking at, antinode that we're looking at. Let's just call that N4 for now. That's going to be this angle right here, theta. Now, if I do a little bit of math, a little bit of triangle geometry here, if this is 90 degrees here, then I can determine what this angle is here. If I know that angle and that this angle down here is 90 degrees, then what happens is this angle that I've drawn here is the same as that angle. It just happens to work out mathematically. If you want to go through, you can find out the mapping. There's a proof for it later. If you want to do a proof for it, you can. Okay, sometimes it's not working for me. Oh, come on. Okay, so those two angles happen to be the same thing. That's good. What we set up here before is that for this to be the fourth bright spot, if I subtract the two lengths of these lines, they need to be 4 wavelengths different from each other to be the fourth bright spot. So if those two lines here, this line here that's kind of going off, this red line, this way and this way, and they converge at that point up there at the same end, that means this distance here, the difference between the two, because from here all the way to there, that should be the same length to the same dot. They convert to that same dot way up there. If that's the same length, then the difference between the two should be 4 wavelengths. If this is pointing towards n is equal to 4, there's a dot way, way over there. Okay? You notice that these two are 90 degrees, so they're kind of parallel to each other. Now what we're going to do is we're going to use this triangle on the bottom here to help us develop a formula. Okay? So the formula set that we're going to make here is going to create a triangle. Well, what do we have here? We have here's my angle. Here's my 90 degrees over here. So this D here is the hypotenuse of my triangle. And this over here is my opposite of my triangle. So I'm going to create a sine theta is equal to my opposite, which is 4 lambda over my hypotenuse, which is D. I'm going to rearrange this for lambda, because most of the time that's what we're looking for. We're looking for what's the wavelength of the light. So I'm going to times the D up and divide it by the 4. And the reason we have a 4 here is because we're looking at the 4th spot. But in the more general case, the formula is going to be D sine theta, horrible, sine theta over n, where n is the nodes, or the antinode, sorry, is the antinode number. Cool. This is a more general case. This is the formula you see on the formula sheet. Okay, so D being the distance between the slits, so they're generally a really small number, n being the antinode, and the angle theta being measured from the central line over to that nodal point. Okay? Now, there's a few things. If I'm not given theta, what if I'm given a few different things? Like in this picture back up here, I mentioned that there's a few other measurements here, an L and an X. I can use an L and an X to find out what theta is if I'm ever given that, because usually don't measure angles. You measure like the distances, like from the screen over and from the screen over to the dot that you're looking at. So if I can measure those two distances, maybe I can draw it on this picture here. Actually, I'll draw it on this picture here. I can measure these two distances, like this here would be called x, and then I have L. If I want to find theta, XL, opposite, adjacent, tan theta is equal to x over L, and I can use this to ever find theta. So if I ever need to find theta to use in this formula down here, I can use x and L to do so. X being the distance from the central antinode to whatever node or antinode you're looking at, and L just being the distance from the slits to the screen or whatever measuring device is up here. It could be anything. It doesn't even have to be a screen. It could just be a detector that just detects the magnitude of the waves there, like a radar detector or something, a microwave detector. Who knows? It could be anything. Okay? So I can use those in conjunction with each other to solve this question here. I'm having problems with this thing. Okay, there we go. So theta, I'm just going to write this down here. Tan theta is equal to x. So all of this. Now, tan theta is equal to x over L is not on your formula sheet. It's just something that you're going to have to know. And again, this makes an assumption. You can only use this as a formula if the distance from the screen, the distance of the measuring device, the top here, to the bottom, if this distance is gigantic compared to how close those D's are. And they're usually really close. You can see from this picture. If lambda is like in nanometers, and this is kind of drawn to scale, these would also be like in nanometers as well, or micrometers. So pretty small distance there. Okay. So we're going to use this formula to solve the next few questions here. And then we're going to get to a couple of questions here where we're going to talk about the other formula. I'm not going to derive the other formula. We're going to talk about the other formula and why it's not a good idea to use it in the next video. Yeah, because I don't want this video to be too long. So I'll see you then. Bye.